Okay, good morning everybody. We are on lecture 7 today. I'm slightly behind in the class, like maybe about half a class behind, so I'm going to try to speed up just a little bit. So I know sometimes many of you try to write down notes in class, so I may not be able to give time for that in the next, say, couple of lectures. So because everything is posted, please work with me, and you can go back and backfill with what's posted. Okay, so last class where we stopped was we talked about how velocity distributions vary with angle of attack for an airfoil. And we talked about how, because pitching moment about the aerodynamic center is a constant, it doesn't change with angle of attack, that is associated with how the velocity distribution changes along the airfoil, right? So it changes much more rapidly near the leading edge as you increase angle of attack than at the trailing edge. So while we are on the topic of pitching moment, we are actually going to try to connect airfoil behavior with aircraft behavior. And so what we're going to do now is we're going to look at an aircraft configuration where the aerodynamics and the longitudinal stability and control behavior. So all of this is determined primarily by the wing. And more specifically by the airfoil. Okay. Any guesses what I'm going to talk about? Pardon me? Yeah, it's a flying wing, and especially an unswept flying wing. A flying wing is another name for a tailless aircraft. I think there are some subtle differences between the two, but for our purposes, they're the same. So this is an example of this. Is the AeroVironment Helios. I showed a version of this airplane in the first lecture when we talked about this solar-powered flying wing. So this aircraft, if I just want to make a rough sketch of it, it looks like this. And it's got many, I forget how many, but something like 14 or something of that sort. Electric motors and propellers distributed along the span, and it also has pods for various avionics and stuff like that. This is just a sketch. You can find pictures of it on the internet. So the top was covered with solar cells, and this was funded by NASA. And the idea was to go and develop a platform that can go up to very high altitudes, 100,000 feet, purely on solar power and do atmospheric measurements. There are a lot of concepts like these that keep coming up, and for a while DARPA wanted airplanes that can go and fly for years without coming down to land or refuel or anything like that. So those are the sort of opportunities one can have with solar powered vehicles. If you can get a solar powered vehicle up to altitude above the weather, essentially if you design them right, they can fly forever, especially during the summers, right, when you have long period of sunshine every day. So this thing will recharge as well as climb up to altitude, and then at night it will descend because it doesn't have solar power. It will descend and maybe use batteries, but then in the morning again it will keep flying. So this is an airfoil. The Helios is a flying wing, right? Essentially there is no tail, there's not even sweep to the wing. It's just a constant chord, unswept flying wing. And so this is an aircraft configuration. So this is an aircraft configuration in which the airfoil quarter chord pitching moment coefficient has to satisfy certain constraints. And that dictates the airfoil design. So how do we make something like this fly? It has to be in stable flight, it has to be in equilibrium, but it doesn't have a tail, right? So that's the challenge. So let's quickly review what is the pitching moment of relevance to an aircraft, and the pitching moment that's relevant for aircraft stability and control kind of calculations is the M about CG, pitching moment about the CG. So let me draw a generic aircraft. And let's say the CG is here, and we've sort of seen this before. This is the x-axis along the body, so these are the body x, y, and z axes that I'm drawing. Y-axis goes to the right, and z-axis goes to the floor of the airplane. And what we are interested in is the pitching moment about the CG. So it is this pitching moment. So MCG is positive as shown here. So this is the MCG is the pitching moment. Due to the aero loads. About the CG. Or in other words, it's about the YB axis. So positive MCG means, by sign convention, the MCG is positive when the moment is about the positive y-axis with the right-hand rule. So this is just to quickly recap what MCG is. Now let's think about what we need to do to have flight at a steady condition and have an aircraft that's stable. Okay, so the requirements for So what I mean by steady flight condition is we want an aircraft to be flying at a constant angle of attack that is maintained naturally. So we need to satisfy a couple of conditions. Okay, so the first condition is we need to have the aircraft be in longitudinal equilibrium, and for that the condition is MCG equals 0. And we saw this in the last class. This means this is same as saying that the center of lift, which is also the same as center of pressure, and the second condition is static longitudinal stability. So these two are different, they are distinctly different. One is equilibrium, one is stability. So the meaning of static longitudinal stability is that if you have a perturbation from the equilibrium angle of attack due to some external disturbance, it might be a gust, it might be somebody walking around in the airplane or something like that, the airplane should naturally return to that equilibrium alpha. Or it should try to return, it should tend to return. That is static stability. Dynamic stability determines whether it eventually returns or not. But static stability means if there's a perturbation, it should try to come back. So if there's a perturbation, the aerodynamic pitching moment should be such that about the CG. So pitching moment about the CG should be such that the airplane tries to come back to the equilibrium alpha. So if I use this airplane as an example, if it's flying along at a constant angle of attack and there's some disturbance, so there's somehow the alpha is increased, then the restoring pitching moment, which will usually be due to the tail on an airplane like this, the tail load will be such that it tries to make it come back. Dynamic stability will determine the eventual motion. So it's like a mass spring damper. So if it gets disturbed, it'll do some oscillation, and if the oscillation is damped, it will return eventually to the equilibrium alpha. But static stability is not concerned with that. It only says it should try to come back. It should go in that direction. So to put the same thing in picture form, let's say you have an airplane here flying horizontally at this angle of attack, which in this picture is very large, but I'm drawing it at a large angle just for clarity. So if it's flying in equilibrium, this is mcg. mcg will be 0, right? It's in equilibrium. So a little while later, if there is some disturbance, so now alpha becomes alpha plus delta alpha. Then this pitching moment should be such that it causes a restoring moment, so alpha will come back to the original alpha. So what should the pitching moment become? So here it was 0, what should we have it here? Positive pitching moment will make the airplane go more nose up, right? This is positive.
The gust will cause a positive movement, so we need a negative movement.
No, so the gust, correct. So somehow the alpha is increased. We're not too worried about exactly what happened that made the alpha increase. What we are worried about is, once it has increased, what do we want the pitching moment to become? Negative, right? So we need it was 0 here, now we need it to be negative. So for this, so for static stability, we need dmcg over d alpha to be less than 0. That means if the alpha increases due to a perturbation, mcg should be negative, but if the alpha decreases, mcg should be positive. Okay, so so now we can list the two conditions that have to be satisfied. So the two conditions are, 1 mcg equals 0, and this is for equilibrium. And in stability and control terminology, it's also called trim. The airplane is said to be flying in trim, which means equilibrium. It's just another word for it. The second one is dmcg over d alpha should be less than 0, and this is for static stability. Okay, so these are the two conditions, and this is for any airplane. Not just for a flying wing. And usually this is not a problem at all because the tail takes care of it. The tail is a small wing essentially, and it's put so far behind that, even if you can adjust the tail lift to a small amount, it will cause a big moment about the center of gravity. So that's not a problem at all. But when you want to make a flying wing work, you don't have a tail, so you have to figure out how to do it. So in this course, what we are going to look at is an unswept flying wing. Because an unswept flying wing is one in which the airfoil characteristics essentially are the wing characteristics for this kind of stuff we are discussing. If you have a swept flying wing, then you can do some other things. You have additional degrees of freedom, and that's the sort of thing we talk about in the wing theory course, where we use wing twist to achieve some of the same things we are trying to do here. But in an unswept flying wing, that doesn't help. So unswept flying wing with a constant chord. Here, essentially, the airfoil properties can be taken as the wing properties. And I'm only talking about this for the purposes of stability and control. So for example, you can't take the airfoil drag, and that's not the same as wing drag. But for stability and control, we can do this. Okay, so because the airfoil essentially controls the stability and is essentially the one that's determining the stability and control, let's look at the aerodynamic forces and moments on the airfoil and see what we have to do. So I'm drawing a generic airfoil. Let's say this is the airfoil for a flying wing. Very soon we'll come to see what special things we have to do to make this work. But for now, I'm just drawing a generic airfoil. Okay, let me draw the chord line. And somewhere here is the quarter chord. And at the quarter chord, if I put the lift, and let's say this is V infinity, and some angle of attack alpha, so this angle is also alpha. If I want to put all the forces on the airfoil, all the aerodynamic forces, and let's say this is inviscid flow, so there's no drag. Okay, so what else do I have to do when I put this at the quarter chord? Is this complete? Yeah, you have to have the moment, right, to make it statically correct. You have to have the moment. The only time you don't have to put the moment is if you're putting this force at the center of pressure, which we are not doing. We are putting it at the quarter chord, so you have to have the moment, and the moment is moment about quarter chord, mc over 4. Now let's say the CG is located somewhere. I'm just going to put it at some arbitrary location. And let's call this XCG. So you can also calculate the moment about the CG. You can calculate moment about any point, right? You can calculate moment about this point, which is essentially this moment plus the force times moment arm. But like we just saw in the previous few slides, moment about CG determines the stability and control behavior, so that's what we are interested in. So we want to calculate moment about CG, and I'm drawing all moments with the positive sign convention here, right? So this is positive. Okay, so a couple of assumptions. So we are assuming we're going to assume lift acts normal to the chord. So in other words, lift is approximately equal to the y force. Right, you can see here lift is not normal to the chord, it's perpendicular to V infinity, but we are going to make this assumption as we go to the next few steps. The other assumption is that CG is at the same vertical location as the airfoil chord line. For an aircraft like the Helios, this is pretty much going to be satisfied. But there are some other flying wings where the CG is not at all at the chord line. Can you think of any of those? What kind of flying wing can you think of where the CG is not at the chord line? It's actually vertically it's very well separated from the chord line. Hang glider, yeah. So hang glider is a flying wing where the CG is well below the chord line. So in that case, you'll have additional terms, and in fact a hang glider makes use of those kind of terms to help achieve some amount of equilibrium and stability and stuff like that. So we are not going to talk about those right now. We'll just go for the conventional unswept flying wing. It's also, some people call it a plank flying wing. It's like a plank. People have come up with all kinds of names. So we now have to let's write the expression for the moment about the CG. So we want to write the moment about the CG. So mCG. So anytime you write the moment here, it is this moment plus the lift times moment arm, right? So mCG is mc over 4 plus L times xCG minus c over 4. So this moment arm is xCG minus c over 4, and the mCG carries over. Okay, so now we divide by half rho v infinity squared s c bar, because we want to write this as moment coefficient. Here S is wing area, wing planform area. That's usually the area used as a reference area for defining coefficients, lift, drag and moment coefficients. And C bar is the mean aerodynamic chord. And this is the reference length that's usually used to non-dimensionalize pitching moment. And in our case, this is equal to chord of the airfoil. So, because we have said we are looking at a constant chord, unswept flying wing. So the chord is constant. So when we do this, when we divide by this, the first two terms become pitching moment coefficients. So CmCg on the left equals CmC over 4, the first term on the right, plus, I should put capital M because we are talking about the aircraft, plus CL times XCG over C minus 1/4. This is for the aircraft. And we can write the same thing for the airfoil, and we'll use lowercase m and lowercase l. So this is going to be our key equation. And 2 pages back, we laid out the conditions we need to satisfy. So this is going to be a critical driver for what we are doing with the unswept flying wing. Okay. So the two conditions are stability and equilibrium. So let's take stability first because it helps us simplify the equation, and then we'll go satisfy equilibrium. So to achieve static stability, the condition is dCmCg over d alpha should be negative. Or equivalently, dCmCg over dCl has to be less than 0 because dCl over d alpha is greater than 0. Okay, so let's take this expression and take the derivative with respect to CL. So we have dCmCg over dCl, which is what we want to make negative, right? So that's the left hand side. So we take that first term becomes dCm C over 4 over dCl, And the second term simply becomes xcg over c minus 1/4 . Okay, what can you say about any of these terms? First term is 0 because? Yeah, so the quarter chord is the aerodynamic center for an airfoil, and by definition pitching moment does not change with lift coefficient when the reference point is the aerodynamic center. Okay, so our dCm/CG over dCl is simply this. And because we want this to be less than 0, we come up with the condition that so for static stability of an unswept wing, what do we do? What do we have to do? If we want to make this negative, what do we have to do? No.
xcg over c must be greater than less than 1/4.
Correct. So you're jumping to the other condition. You kind of like know the answer. So but that's a sort of, that's why I'm trying to emphasize there are two explicitly different conditions. For one thing you have to do some, let's call it A, and the other thing you have to call it B. What you have to do is B. But after some time, most of us kind of mix these two up and say you have to do B for this and A for that. You kind of make the connection the other way. So if you have to, just from the equation, you almost have to throw away things that you know and say, looking at this equation, what can I say? To make this negative, this has to be negative, right? So that means xcg over c minus 1/4 has to be less than 0, or cg has to be forward of the quarter chord location for an unswept flying wing to be statically stable. Nothing about reflex trailing edge, right? Not yet. But that's coming up right away because we have the other condition. For equilibrium of a statically stable flying wing, well, let me scratch this off. For equilibrium, we want CMCG equals 0. Now, so even without talking about a flying wing, we can say, what is CMCG? we just wrote that equation like 3 pages back. CMCG is this. And this has to be equal to 0. Otherwise, you're not flying in equilibrium. Now, most of the time we want to fly at positive lift coefficient, right? Unless there's, for aircraft anyway, most of the time you're flying at positive lift coefficient. So this is positive. Lift coefficient is positive. What is this? What can you say about this term? This is negative. For static stability, we just showed a minute back that this is negative. And this is for a statically stable flying wing. But we want the total to be 0. So this product is turning out to be negative. So what can you say about this? Has to be positive. And this is only if you have static stability. Right? So if for some reason you design an aircraft that's not statically stable, then you could make this positive. You could put the CG behind the quarter chord. You can have both this whole product positive, and you can put a negative. You can work to have the CMC over 4 negative, and you can still achieve 0. Is it even, does it make any sense to talk about an aircraft that's not statically stable? Can you think of examples? No? Come on. I mean, not just flying wings, anything, any aircraft that's not stable. You can, right? If you have stability augmentation, you can have a closed loop system. You can have a, what do you call those? Pardon me?
Fly-by-wire.
Yeah, fly-by-wire is more the mechanism by which the controls are moved. But essentially you can have a controller that senses that the aircraft is going away from the trim angle of attack, and then it will actuate the elevator and bring it back. So it will do this many times a second to artificially keep it stable. So it's not naturally stable, but it's artificially stable. So I think many fighters are like that because they want maneuverability. They sacrifice on stability. And so the computer is essentially changing the elevator many times a second to keep it in at the equilibrium angle of attack. And if you turn off this stability augmentation, this airplane might be pretty difficult to fly. It's not impossible to fly. Marginally unstable airplanes, people can still fly. It has to be, there are other conditions that has to be satisfied, but a pilot has to be, it's a lot of pilot workload. The pilot's all the time keeping angle of attack at the desired value. Whereas if it's a very nice and stable airplane, you can take your hands off the control column and do other things, operate radios or look at the map or something like that, and the airplane will still be flying at a fairly constant angle of attack. Anyway, we are talking about statically stable flight. So it turns out that the pitching moment about the quarter chord for the airfoil has to be positive, otherwise you can't have equilibrium. Okay, so what we see is that so you require positive CM if all of these conditions have to be met. So it has to be flying in positive CL and it's statically stable. So what's the big deal about this? The reason this is kind of important and something to really keep in mind is because conventionally cambered airfoil is like this, right? This is a conventional cambered airfoil. What's the pitching moment for these airfoils? Negative, right? So these airfoils have negative pitching moment. Most airplanes have these kind of airfoils. So if you take an airplane like this, the airfoil pitching moment will be negative. CMC over 4, or in other words, CMAC is negative. So you cannot use an airfoil like this for the situation we are talking about because we want positive pitching moment. We're talking about pitching moment about the quarter chord, which is the aerodynamic center. So what can we do to have a positive pitching moment? This is where your answer is applicable, right? Yes. So you can, you want positive lift, right? So you want the overall lift of the airfoil to be positive, but you want positive pitching moment also. So one way to do that is to create a small downward force near the trailing edge, and this moment arm is pretty large, right? So if you have a small downward force, it will create a nose up moment, which is a positive moment. So rest of the airfoil can create positive lift. If you can create negative lift near the trailing edge, you can adjust the pitching moment to be positive. In fact, that's what you do on an airplane too. In many circumstances, if you want positive pitching moment about the neutral point. So we are kind of jumping some steps. But the easiest way to do that is to have a small negative load at the tail, and because you have such a large moment arm, it works out. So So if you can have a small down lift, down force near the trailing edge, So that's what a reflexed airfoil does. So a reflexed airfoil looks like this. So the airfoil is designed with positive camber, but right at the trailing edge, it's got a upward tilted trailing edge. It's got a negative camber. And if you draw the CP distribution, we're going to try to connect as many things as possible to CP or velocity distribution. That way we can start interpreting what these CP distributions do and talk about what that will mean for the airfoil characteristics. So here you might have an upper surface velocity or CP distribution that looks like this. And then it will come down and do this, whereas the lower surface might be something like this. So this is upper surface and this is lower surface. It's just a sketch, so it may not look exactly like this, but something along these lines. So we talked about how the area between upper and lower surface is the lift, right? So if you take any portion along the chord, if you take a small piece of the airfoil, this difference in CP distribution between upper and lower is the amount of lift, the area. This area is what determines the local lift over this piece of the airfoil. Now, towards the trailing edge, because you have shaped the airfoil in this fashion, the curves flip. So if the upper surface curve is lower than the lower surface curve, if you plot it like this, that means the lift is negative. So in this region, for example, there's going to be downward lift. And in fact, all over this portion of the airfoil, there is some sort of down lift. And that the telltale sign in the CP distribution is the curves flip around or cross over near the trailing edge. Okay, so this is called a reflexed airfoil or reflexed trailing edge. So you essentially, if you're building the airfoil, let's say out of balsa wood or something, you can, if you turn the trailing edge a little bit up and apply steam or something so that the shape becomes permanent, then that will be a reflex trailing edge airfoil. Okay, so there are some other ways to do the same thing, but essentially the same idea. You can have a symmetric airfoil and have upward flap deflection. So many airplanes, not many, but there are several airplanes where they do this. Most wings have some sort of flap in the back, right? So if you design a wing with a flap and aileron, and you want to make it a flying wing, you can turn the flap up. So TE flap up. And this is called a negative flap angle. You can do this even with a cambered airfoil, except you'll need more up flap deflection for the same kind of pitching moment, desired positive pitching moment. So you'll have more up flap deflection. Some years back, somebody in this course came up with the idea or came up with the question that can you take a cambered airfoil and put it upside down? Will this work? So a traditional cambered airfoil causes nose down pitching moment, right? So if you flip it, it's going to cause nose up pitching moment. So this will also work. Why don't we do this? I mean, why don't airplanes have, flying wing airplanes have upside down cambered airfoil? It's going to be pretty inefficient. It's really designed for generating lift like this, right? That's what now you're putting it upside down and asking it to generate like this. It'll do it, but it's inefficient, and you're going to see that in homework 2, I think. Yeah, homework 2. But the preferred approach is to have a reflexed airfoil. It looks like this. And this is the preferred. Okay, there's a quick story I can talk about when this upside down cambered airfoil actually played a role. So I have a good friend and collaborator actually in the Raleigh area. He's an NC State grad, and he's an expert RC pilot. He flies in competitions, and he's actually a sort of professional RC pilot who goes and flies for big companies when they have UAVs and so on. And he also goes to these races. So they make these giant scale RC airplanes, and they fly it around pylons. There are a bunch of people all around the US and even the world who go to races, and they want to win the race, right? So these are races where there will be airplanes that are flying in close quarters because they're all racing around a race course. And they're all flying really close. So one of those races, another airplane came really close, and these two collided and cut off this guy's airplane. So let's say this is that airplane, and this other airplane came, and the prop cut off the tail, the empennage of this airplane. So this whole thing fell away, right? So it's only, and this is all happening so fast. These airplanes go at something like 200 miles per hour or some ridiculous speed. They're going zoom, zoom, zoom around you've got to be a really good pilot, and this friend, his name is Robert Wess. He's been flying for so many years that he's got all this intuition about flying, right? So he didn't want to lose the airplane. I mean, the tail has fallen off, but these are fairly expensive stuff, and he's got all kinds of radios and stuff inside. He didn't want the whole thing to crash and burn and be a complete loss. So just instinctively, I mean, there's no time to do any kind of calculation or anything. just instinctively. So imagine the airplane is here and the tail is gone. So instinctively he turned it upside down, and immediately he could at least get some semblance of control, and he was able to actually come down and land it in a sort of recoverable state. So he lost the tail, but everything else came down and landed. And he had a video, and I'm not able to get the video. I think he's lost the video. I've been asking him for it. My guess about what happened is that if an airplane is not in equilibrium, you can't fly it, right? So stability, if you don't have it, you can manage, but equilibrium you just have to have. Otherwise it's going to go nose down like this or nose up like this or something. So my guess is the CG was more or less in front of the quarter chord of the wing, and instinctively when he turned it upside down, it became a stable sort of flying wing. So it's a cambered airfoil, regular cambered airfoil. He turned it upside down, it became this. Now he's got equilibrium, because you have to have positive CMC over 4 for equilibrium. And I mean, even if it's not stable, it was just for a short flight. It was coming down to be a controlled crash, and he was able to do that. And it's just cool that he did something and it was instinctive and he got it down, whereas normally this thing would have been a total wreck. Okay, so you're actually going to look at these things in homework 2 as part of other, along with some other things. So you'll have opportunity to go back and look at this. Any questions quickly? Okay, so that's about connecting airfoil to aircraft flight, right? Stability and control. And the really good example relevant to how an airfoil connects to aircraft is the flying wing, because the airfoil itself is the airplane in some ways. So we are now going to talk about, so all of this takes into discussion lift and pitching moment. We've been kind of ignoring that other force, the drag, right? So now we are going to start talking about drag. And all this time we have also been connecting CP distributions or same as velocity distribution on lift and pitching moment, right? We just haven't talked just about lift and pitching moment. We've been connecting the CP distributions. So what we're going to move on now to is what CP distributions can tell us about drag. So it turns out for drag also, CP distributions are major drivers. And the reason for that is because the velocity or the CP the gradients of these distributions affect boundary layer growth. And the boundary layer in turn determines the drag coefficient. We'll be talking about boundary layer so much that I'm going to start writing BL for boundary layer. And the boundary layer growth also determines CL max. So how the airfoil stalls is all completely determined by the boundary layer. So because of that, we are now going to talk about boundary layers. So this is a very deep subject. There is a whole course in the undergrad program called boundary layer theory. Anybody taken boundary layer theory? That's it? Nobody else? It's an elective now, right? So, okay. So it's a whole course, and you can do much more than a course. There's books on boundary layer theory, and people still continue to do PhDs on small aspects of boundary layer theory. So there's just lots you can talk about it. Our course is not a boundary layer theory course. We are just going to look at boundary layers in an overview form, enough to be able to understand how they affect airfoils and what you should do to get good boundary layer characteristics. So let's talk about what a boundary layer is. As always, I'm going to draw an airfoil, but now I'm going to draw a boundary layer on top of this airfoil in a different color. So this little region, the thin layer on the surface of the airfoil, is called a boundary layer. Who came up with the concept of boundary layer? Prandtl, right? So Prandtl is many ways like the father of aerodynamics, if you can say. He came up with so many, superb insights that a lot of our understanding of aerodynamics today is traced to those insights. Boundary layer theory, lifting line theory, he explained what is the difference between a wing and an airfoil through lifting line theory. And then boundary layer theory and many others. So what is happening in this thin layer? So let's kind of zoom into this and take a look. So if this is the surface, and I draw a line normal to the surface at this point. Because of viscosity, the flow velocity relative to the surface is 0 at the surface. So V equals 0 at the surface due to viscosity. And this is called no slip condition. So this is in real flow. Often we'll go to the approximation of inviscid flow, and that's just to make calculations easy. It turns out for many purposes inviscid calculation is good enough. But real flows are viscous, and because of viscosity, velocity will become 0 at the surface. But as you go normal to the surface outward, the velocity will start increasing. The flow velocity will increase until at some point it reaches the edge velocity. And after that it stays at the edge velocity, at least for some distance, and then you have inviscid flow effects taking over. So, but in the vicinity of this is the edge velocity. So UE is the edge velocity. And in your homework 1, in the programming assignment, you have this data files, and one of the columns is UE, and that UE is really this edge velocity. And this region is called the boundary layer. So this is the boundary layer. So it's the small region near the surface inside which the velocity goes from 0 to edge velocity. And this thickness is called delta. This is called boundary layer thickness. So let's plot this in a larger scale, and the plot is going to look like this. So this is, I'm going to plot it in non-dimensional form, U over UE versus Y over delta. Okay, so UE is the edge velocity. So if you go from 0 over here, U will become UE, so that U over UE will be 1. And at that place Y, so Y is this coordinate. Y is the normal direction coordinate, and when Y equals delta, Y over delta is 1. So this is the edge of the boundary layer. At the edge of the boundary layer, these two become 1, and the velocity increases from 0 here to 1 at the edge of the boundary layer, and after that it stays at UE. So this is the edge of boundary layer. And this diagram is called a velocity profile diagram. So we'll have many similar sounding terms, right? So we are talking about velocity distribution. We have been talking about that earlier. That's like a CP distribution. That is how the velocity varies from leading edge to trailing edge on upper and lower surfaces. Something similar is velocity profile. It sounds similar, but it's very different. Velocity profile is how the velocity varies inside a boundary layer. Okay, so we'll stop here and resume on Tuesday next week.